I am Dr.S.Prasanna, Assistant Professor of Mathematics in Pingal Government College for Women, Warangal. Today, let us solve some problems on span and subspace spanned by a set. So, before solving the problems, let us recall the terms span and subspace spanned by a set. Span is a set denoted by span of v1, v2, so on vp, and it is defined as the set of all linear combinations of the vectors v1, v2, so on vp. And this span of v1, v2, so on vp, that is a set consisting of, in set builder form we can see here below, it is the set consisting of vectors gamma bar such that gamma bar is equal to c1 v1 plus c2 v2 plus so on cp vp, where c1 c2 so on cp are scalars. So span is the set of all linear combinations. If you recall, that looks like gamma is equal to c1 v1 plus c2 v2 plus so on cp vp. So all such vectors, all those linear combinations, lie in the set span of v1 v2 so on vp, and that is how span of v1 v2 so on vp is called as the linear set of all linear combinations of the vectors v1 v2 so on vp. Now subspace spanned by a set, that is defined like this. Let H be a subspace of a vector space V. Then a spanning or generating set for H is the set consisting of the vectors v1, v2, so on vp in H, such that H is equal to span of v1, v2, so on vp. That means H is a subset of V, the vector space V first of all, and it consists of all the linear combinations of the vectors v1, v2, so on vp, and it is a subspace of the vector space V. And we have also seen that we have also proved the statement for two vectors, that is, if H is equal to span of v1, v2 is a subspace of V, then we have proved that H is a subspace of V. That is, H is equal to span of v1, v2, then it is a subspace of V, where V is a vector space consisting of the vectors v1 and v2. So by verifying the conditions for a set to be a subspace, we have proved that H is equal to span of v1, v2 can be a subspace of the vector space V. And we have even extended this logic to more than two vectors and came to a generalization that V1, this is true, that is span of v1, v2, so on vp is a subspace of the vector space V when v1, v2, so on vp are vectors in V. Now we can see some illustrious examples based on this theorem. The first problem goes like this. Let capital H be the set of all vectors of the form S, 3S, 2S. It is a column vector consisting of three vectors S, 3S, 2S. And now it is asked that find a vector V bar in R3 such that H is equal to span of V bar. And we have to show that H is equal to span of V bar first of all, and it is also asked further that is H a subspace of R3. As we can see, the set H consists of all 3x1 vectors, then that shows that H is a subset of R3. Now our aim is to prove that H is a set of all linear combinations of the vector v bar in R3, and also we have to show that H is a subspace of R3. For that, how we can proceed? Let us see. Given H is the set of all vectors of the form S2, S, 3S. So H is a set, given that in the problem itself, that H is a set of all vectors of the form 3 by 1 column vectors with the entries as S2, S, 3S in the column. So this is 3 rows and 1 column. We have to understand that every element of H consists of is a column vector, or we can say it is a matrix where there are 3 rows and 1 column. Now if we write this H in set builder form, we can, or in notational form, we can have H is equal to set of all elements, set of all column vectors consisting of the entries S2, S3, S in column, such that S is a real number. S is belonging to the set of real numbers. With the definition of this set H, we can understand that H is a subset of R3. That means every element of H is a 3 by 1 column vector, which is a single vector, or we can say it is an ordered triad in if we look it in 3-dimensional geometry, so that H is a subset of R3. And we have already come across it that in the prerequisites itself, R3 is viewed as vector space in the study of linear algebra. So that is how R3 is already a vector space, and now that H is a subset of vector space R3. Given that S2, S3S is an arbitrary element of H, and H is consisting of the elements of the form S2, S3S. That means S2, S3S for an arbitrary real number S gives some arbitrary element of H. That is how S2, S3S can be any element of H depending on the value of S that we are taking. S should be taken from the set of real numbers. Now I am considering that column vector, that arbitrary element of H, and writing it as S2S 3S is equal to S times 1, 2, 3. This can be done by, as S2S 3S is a column vector in H and H is a subset of R3. That is how this S2S 3S will be an element of R3, and we have seen that R3 is a vector space, and wherein the scalar multiplication is valid, is existing. So that is how S times 1, 2, 3, which is the scalar multiplication, gives us S2S 3S. So I am using it in the reverse way and getting that S2S 3S is equal to S times 1, 2, 3. Now this is, I am expressing this as S into V bar. Whatever the column vector we are getting after taking S in common, or S as scalar outside of that matrix or column vector, that column vector which is here, it is 1, 2, 3, and that vector I am representing it as V bar. So V bar is 1, 2, 3, and here S means it is a real number. So as it is a real number, we can treat it as a scalar, and so that S2S3S is now equal to SV bar, where V bar is a vector and S is a scalar. So that is how SV bar is a scalar multiple. We should say it is sum of scalar multiples of V bar, and the sum of scalar multiples of V bar is called linear combination of V bar. So that is how it is equal to, further it is equal to linear combination of V bar. That means S2S 3S, which is an arbitrary element of H, is nothing but equal to, is nothing but can be expressed as linear combination of V bar. That means H is equal to span of V bar, where span of V bar means that it is a set consisting of all linear combinations of V bar. So span V bar is the set of all linear combinations of V bar, H should be equal to span of V bar, as we are taking any linear combination. SV bar is any linear, can be any linear combination of V bar by varying values for S in the set R. So that is how H is equal to span of V bar. Hence H is a subspace of R3. By the above theorem, in the what we have proved in the previous video lesson, therein we have seen that if V1, V2 are any two vectors in a vector space V, then span of V1 comma V2 will be a subspace of V. So that is how here also H is equal to span of V bar. That leads us to the conclusion that H is a subspace of R3, as here the vector space is R3. So we could prove that in this, we could show that in this problem H is a subspace of R3. Now let us move on to the next problem, second one, and it goes like this. Let H be the set of all vectors of the form 2t 0 minus t. Show that H is a subspace of R3. Here we are given a column vector of the form 2t 0 minus t. These are the entries in the column vector. Now this column vector is in the set H, and our task is to prove that H is a subspace of R3. For this we need not verify the subspace conditions for H. Instead we do that H, which is a set of elements of the form column vectors of the form 2t 0 minus t, where t is a variable and takes the values from the set R, set of real numbers R. That set H can be equal to the span of some vector, So we should now be able to deduce some vector V bar, so that H is equal to some scalar multiple of that vector, and so that H can be equal to span of that vector, and by the above theorem again we can conclude that H can be a subspace of R3. So for that, let us go with these steps. Given H is a set of all vectors of the form 2t 0 minus t. Now H is equal to set consisting of the vectors, column vectors 2t 0 minus t, such that t belongs to capital R. Here t is a real number. By this definition of H, we can understand that H consists of all 3 by 1 vectors, where t is a real number. That means H is a subset of R3. So R3 is set of all 3 by 1 vectors, and H is the set of vectors of the form 2t 0 minus t, where the second entry in the column vector is always 0. That is how H can be a subset of R3. Now any arbitrary element of H is of the form, can be considered as of the form 2t 0 minus t, where t is a real number. So any arbitrary element depending upon the value of t, that vector, column vector gives us some element of h. So in general 2t0 minus t can be any element of h for some t belongs to R. Now I am taking 2t0 minus t and taking t common, we get t times 20 minus 1. This is scalar multiplication in the vector space R3. As I said in the previous problem, R3 should be viewed as a vector space and wherein the scalar multiplication holds good. That is how we can write 2t0 minus t as t times 20 minus 1. Now I am considering the vector, column vector 20 minus 1 as v bar. So we are naming the column vector 20 minus 1 as v bar, so that 2t0 minus t will now be equal to t v bar, where v bar is equal to the column vector 20 minus 1. And here we should remember that t is a real number, so that it can be treated as a scalar, and further t v bar is a sum of scalar multiples of v bar, and that is how it is a linear combination of v bar. So finally we could show that 2t0 minus t, which is an arbitrary element of h, can be expressed as a linear combination of v bar. If some element of h is a linear combination of v bar, then generalizing it, we can say that every element of h can be expressed as a linear combination of v bar. That means h, the set h itself is equal to span of this vector v bar. So h is equal to span v bar, where v bar is the vector that we found as 20 minus 1. So h is equal to span of v bar, and that is how h can form a subspace of the vector space V, where V is the here it is 3 by 1 set of vectors, so it is R3. So H is a subspace of R3. Now moving on to the third problem. Let W be the set of all vectors of the form 5b plus 2c bc, where b and c are arbitrary, and we are asked to find whether W is a span of some vectors u bar and v bar. So our task is to find some vectors u bar comma v bar, so that W is equal to span of u bar comma v bar. So solution. Here it is, the problem is not completely written, but what I have said, just follow that. Find u bar comma v bar, so that W is equal to span of u bar comma v bar. That is the missed part of the question. Now moving on to the solution. Given W is the set of all vectors of the form 5b plus 2c b c. And by this statement, we can write the set W in notational form as W is equal to set consisting of all the column vectors of the form 5b plus 2c bc. It is a 3 by 1 column vector. That means it has 3 rows and 1 column. And the first row element is 5b plus 2c. Second row element is b, and the third row element is c. And all these 3 terms constitute a single column. That is how it is a 3 by 1 column vector. Now in this column vector we are finding 2 variables, b comma c. And what about these b comma c? Where are they considered from? If we see, they are real numbers. B comma c are given real numbers. That is how W is equal to set of all elements 5b plus 2c b c, such that b comma c are real numbers. Now consider the column vector 5b plus 2c b c. In fact, it is an arbitrary element of the set W. And this is equal to B times it is 510 plus C times 201. How could I express this like this? See here, I have taken B common, where when we take B common in the first element, we can see the scalar multiple of B is 5. In the second element, the scalar multiple of B is 1. And in the third entry, there is no B at all. There is no scalar multiple of B at all. By that we have to understand that in the third entry, the scalar multiple is 0. So by taking B common, the column vector that we get besides B is 510. Next, let us plus, and it is further equal to plus C times the first entry. It is we can see the coefficient of C, that is scalar multiple of C is 2. So here I have written 2. In the second entry, there is no C at all. So the second scalar multiple is 0. Scalar coefficient is 0. And in the third entry, the coefficient of C is 1. So that is how B times 1 vector plus C times 1 vector gives you the given vector 5B plus 2C BC. So here we can see two vectors. One is 510 and another is 201. I am naming them as U bar and V bar respectively. So that U bar is equal to 510 and V bar is equal to 201, where B, and in this BU bar plus CV bar, B comma C are real numbers as it is given in the definition of W in the problem itself. So 5B plus 2C BC is equal to BU bar plus CV bar means every vector, that is 5B plus 2C BC, is nothing but a linear combination of U bar and V bar. If this vector that we have taken is an arbitrary element of W, we can say that every element of W is a linear combination of U bar and V bar. That means W is just equal to span of U bar comma V bar. Therefore, if W is equal to span of U bar comma V bar, by the theorem that we have proved earlier in the previous video lesson, which states that if V1 comma V2 are two vectors in a vector space V, then H is equal to span of V1 comma V2 is a subspace of V. So that H is equal to span of V1 comma V2 is a subspace of V whenever V1 comma V2 are vectors in V. Using that, here in this problem, we have arrived at solving the problem. We have arrived at W is equal to span of U bar comma V bar, and using that theorem here at this juncture, we can conclude that W is a subspace of R3. It is written here R2, it's not R2, R3, as every vector in W is 3 by 1 column vector. So W is a subspace of R3. Next, moving on to the next problem, let W be the set of all vectors of the form A minus B, B minus C, C minus A, B. Even though there are so many variables, these constitute only 4 rows, 1 column, and that is how it is a 4 by 1 column vector, where A comma B comma C, those 3 variables represent arbitrary real numbers that is given in the problem. Now we are asked to find a set S of vectors that span W, or give an example to show that W is a vector space. So to show that W is a vector space, we should show that W is equal to span of some vectors. And if W is equal to span of some vectors from the original vector space R4, then W can be treated as a subspace of that vector space. Here in this case that vector space is nothing but R4, because every vector in W we are taking as 4 by 1 column vector, and all the 4 by 1 column vectors are the elements of R4, and by prerequisites of this chapter of this subject we know that R4 is a vector space. Now coming to the solve the problem, the first point we have to take write as W is the set of all vectors of the form A minus B, B minus C, C minus A, B, which is given in the problem, where it is also given that A, B, C are arbitrary real numbers. All this matter we can represent in the notational form for the set W as W is equal to set consisting of the column vectors 4 by 1 column vectors A minus B, B minus C, C minus A, B, such that A comma B comma C belongs to capital R. Now consider this arbitrary element as A, B, C are arbitrary real numbers. That means ABC can be any real numbers. Then A minus B, B minus C, C minus A, B gives any column vector or any element of the set W. As W is consisting of all the 4 by 1 column vectors, it can be treated as a subset of R4 first of all. Now consider this arbitrary element A minus B, B minus C, C minus A, B of W, and this we can write as split as scalar multiples of 3 vectors. And how it is done, see here. Taking A common, we can write the vector besides A as 1 0 minus 1 0, because in the first element, in the first entry of 4 by 1 column vector on left hand side, we can see the coefficient of A is 1. In the second entry, the coefficient of A, there is no A at all, so it is treated as 0. In the third entry, the coefficient of A is minus 1, and in the fourth entry, the coefficient of A is 0, as there is no A at all in the fourth element. Now taking B common, plus B we should write, plus B times, in the first element B coefficient is minus 1, in the second element it is 1, in the third element there is no B, so it should be 0, and in the fourth element that it is B, so the number here it should be 1. Plus C times, now taking C common, excuse me. Now taking C common, in the first element there is no C, so we should write 0. In the second element it is minus C, so the coefficient of C in the vector it should be written as minus 1, and in the third element it is 1, and in the fourth element there is no C at all, so it should be written as, it should be taken as 0. Now whatever be the column vectors that we have seeing besides A, B, C scalars, those vectors I am naming them as V1 bar, V2 bar and V3 bar. That means V1 bar is equal to 1 0 minus 1 0, V2 bar is equal to the vector besides B, that is minus 1 1 0 1, and V3 is the vector which is a multiple of C above, and that is taken as 0 minus 1 1 0, named as V3 respectively. And here A comma B comma C are arbitrary real numbers. In AV1 bar plus BV2 bar plus CV3 bar, A comma B comma C are arbitrary real numbers. Therefore, let S is equal to, let us take a new set and define that set S as consisting of all these three vectors v1 bar, v2 bar, v3 bar. Then a minus b, b minus c, c minus a, b is equal to linear combination of these vectors v1 bar, v2 bar, v3 bar, as we are seeing here. Any arbitrary element of W can be expressed as AV1 bar plus BV2 bar plus CV3 bar. That leads us to take the conclusion that A minus B, B minus C, C minus A, B is equal to linear combination of V1, V2, V3. That means W is equal to span of V1 bar, V2 bar, V3 bar, or as we have taken that set V1, V2, V3 as S, we can also write as W is equal to span S. So W is equal to span of those vectors, that means W is a vector space. In fact, W is a subspace of R4, and we can understand that W itself is being a subspace, it is itself a vector space. That is how W is a vector space. And S is the set consisting of the vectors v1, v2, v3, where v1, v2, v3 are defined like this. So now time to move for the next problem, fifth one. Let W be the set of all vectors of the form S plus 3t, S minus t, 2s minus t, 4t. This is also a 4 by 1 column vector. Now we are asked to show that W is a subspace of R4. So our aim is to prove that W is a subspace of R4. As I said, R4 is the set consisting of all 4 by 1 column vectors with entries as real numbers, is viewed as a vector space by the prerequisites that we have gone through in the beginning of this subject. Now W is given as the set of all vectors of the form S plus 3t, S minus t, 2s minus t, 4t, and this in notational form can be written as W is equal to set consisting of that column vector S plus 3t, S minus t, 2s minus t, 4t, such that there are two variables present in this column vector, and those two are S comma t are obviously the real numbers. So S comma t are real numbers, and by this definition of W we can understand that W is a set consisting of some particular the 4 by 1 column vectors of such form. So W is a subspace of R4, and we can see that S plus 3t, S minus t, 2s minus t, 4t is an arbitrary element of W. So this arbitrary element, consider it and take S common and then t common, and that means writing scalar multiples of S and t like this. We get S times 1120. This is obtained by seeing the S coefficients in the first, second, third, fourth entries of the column vector present in the left hand side. Similarly, plus t times taking all the coefficients of t in all the 4 entries, writing them in a column vector 4 by 1 column vector besides t, we get it as t times 3 minus 1 minus 1 4. So this is equal to S times some 4 by 1 column vector plus t times some 4 by 1 column vector. So here we got two new column vectors, and those two column vectors I am naming them as u bar and v bar respectively, so that our arbitrary element of w is now equal to su bar plus tv bar, where u bar is equal to 1 1 2 0 comma v bar is equal to 3 minus 1 minus 1 4, and here we can see s comma t are real numbers. So s plus 3t, s minus t, 2s minus t, 4t, that arbitrary element is now equal to linear combination of u bar comma v bar as it is expressed as su bar plus tv bar above, as s comma t are variable numbers, variable values of variable values taken from the set R. We can say that this arbitrary element from W, that is s plus 3t, s minus t, 2s minus t, 4t, can be any linear combination of the vectors u bar comma v bar depending on the values of s comma t from capital R. So W is equal to span of u bar comma v bar, because as this arbitrary element is any linear combination, we can generalize it and say that, extend it and say that W is the set of all linear combinations of u bar comma v bar. That means W is equal to span of u bar comma v bar. That is how W is a subspace of R4. Since if v1 bar, v2 bar are vectors of a vector space V, then H is equal to span v1 bar comma v2 bar is a subspace of V. This is the theorem statement that we have proved in the earlier classes. Now moving on to the next problem, sixth one, that is let v1 bar is equal to 1 0 minus 1 comma v2 bar is equal to 2 1 3, v3 bar is equal to 4 2 6, and w bar is equal to 3 1 2. So there are four vectors, all of them are 3 by 1 column vectors given to us. Now we are asked to find three problems in the bits A, B and C. So in the A bit, it is asked that is w bar in span of v1 bar comma v2 bar comma v3 bar, and in B bit it is asked that how many vectors are in span of v1 bar comma v2 bar comma v3 bar, and in finally in the bit C it is asked that is w bar in the subspace spanned by v1 bar comma v2 bar, if so why. So these are the questions raised to us, and we are given with four vectors, namely v1 bar, v2 bar, v3 bar and w bar. So to start with the solution, we should write the first step as the given vectors, whatever be the content or data given provided in the problem, we should write it, mention it first in the beginning itself. Then using that data, that information, we should proceed to get the solutions of the questions that we are asked for. Now taking we have written v1 bar, v2 bar, v3 bar and w bar, and now moving to the solution of A bar, bit A, the vector w bar be, let us suppose that the vector w bar be written as, can be expressed as a1 v1 bar plus a2 v2 bar plus a3 v3 bar for some scalars a1 a2 a3. So this I am writing in the reverse manner in the next step, and I observe here, I have noticed here, I have taken that statement as equation number 1, taking w bar as a1 v1 bar plus a2 v2 plus a3 v3. Now take this in the other way and write it as A1 V1 plus A2 V2 plus A3 V3 is equal to W bar. Now substitute all the 4 vectors that are given to us in the problem. Those are V1, V2, V3 and W bar. Substituting all these vectors and applying scalar multiplication on the left hand side, we get sum of 3 vectors. A1 0 minus A1 plus 2A2 A2 3A2 plus 4A3 2A3 6A3, and that is further equal to 3 1 2. Now the left hand side, sum of 3 matrices can be written as A1 plus single matrix as of the same order 3 by 1, and it consists of the elements A1 plus 2A2 plus 4A3, which is obtained by just adding all the first row elements in all the 3 vectors on left hand side, and we got like this: A1 plus 2A2 plus 4A3 as the first element, A2 plus 2A3 is the second element, and minus A1 plus 3A2 plus 6A3 is the third element on the left hand side resultant vector. Now this is equal to 3 1 2, which is on the right hand side. As there are, at this point we are left with 2 vectors of same order on either side of is equal to on either side. So these two are equal means the corresponding element should be equal by the definition of equality of matrices. So we get 3 equations like this, and all these 3 equations represent a linear system in the variables A1, A2, A3. So that linear system I have taken represented as equation number 2. Now the system of linear equations in 2 can be written in matrix equation simply as Ax bar is equal to B bar, where A is the coefficient matrix which consists of all the scalar coefficients in the 3 equations in 2, and that is how capital A is a 3 by 3 matrix. And x bar, next one is x bar is equal to the column vector consisting of all variables A1, A2, A3, and W bar is the values that are in the right hand side of those 3 equations in equation 2. So W bar is equal to the column vector 3 1 2. Now the augmented matrix A B bar is equal to 1 2 4 3 0 1 2 1 minus 1 3 6 2. This is obtained by taking the first columns of A as first 3 columns of AB bar, and the last column is just the actually it is B bar, not W bar there, it is B bar is equal to 3 1 2. So AB bar, the fourth column of AB bar is the vector B bar 3 1 2. Now apply some row elementary operations in the augmented matrix and try to change it into echelon form. Echelon form, I have discussed about it in the prerequisites in the beginning of this subject. Applying now operation, I am taking the row operation as R3 as R3 plus R1, and the augmented matrix transforms to the matrix which looks like this: 1 2 4 3 0 1 2 1 0 5 10 5, and this in this we can see that the last row has 5 number in common. So let us divide that last row by the scalar or by the real number 5. Then we get the next matrix as next equivalent matrix as 1 2 4 3 0 1 2 1, and the last row when we divide by 5 we get 1 2 1. So next we can see that the second and third row are one and the same, and let us try to subtract R3 from R2. Then we get 1 2 4 3 as the first row, and 0, 1, 2, 1 as the second row with all zeros as entries in the third row. So let us treat this as the last transformed augmented matrix, and at this stage we can give the conclusion about the solution of the linear system in equation 2. As the last row in transformed augmented matrix above has the last row has all the elements as zeros. The last row has all the elements are as zeros. The system of linear equations in 2 is consistent and has infinite number of solutions. Therefore, that means if the last row of the transformed matrix is a row consisting of all zeros, then we can say that the system of linear equations in equation 2 is consistent and has infinite number of solutions. That means there exist scalars a1, a2, a3 satisfying the linear combination that we have taken in equation 1. That means W bar can be represented expressed as a linear combination of V1 bar, V2 bar, V3 bar. Therefore, W bar is in span V1 bar, V2 bar, V3 bar. As it is a linear combination, it should belong to the set of all linear combinations, which we denote it as span of V1, V2, V3. So that is the solution for the bit A. That means we could prove that the given vector is a linear combination of V1, V2, V3, and that means W bar is in span V1, V2, V3. Now moving on to the solution for the B bit. From A above, we have seen that there exists infinite number of solutions for linear system of equations in variables a1, a2, a3. So the infinite number of solutions means the scalar coefficients a1, a2, a3 in the three equations which are represented by equation 2 have infinite number of values for a1, a2, a3. That means there are infinite number of linear combinations with the vectors v1, v2, v3. If a1, a2, a3 can take infinite number of values, we can say that there exists infinite number of linear combinations of the vectors v1, v2, v3. Thus, span v1, v2, v3 has infinite number of vectors, each of which is a linear combination of v1, v2, v3. So there are how many solutions or how many vectors are there in span v1, v2, v3 is the question asked for us, and now we are saying that span v1, v2, v3 has infinite number of vectors, and each of that vector is nothing but the linear combination of v1, v2, v3. Now the last bit, C bit, says in this C bit we are asked to find whether W bar is a linear combination of the vectors v1, v2. Now let us see, consider v1, v2 the given vectors, W bar is also the given vector. By observation itself, by observing the vectors v1 and v2 and W bar, v1, v2 and W bar, we can understand that when we add v1 bar plus v2 bar, we are getting the vector W bar itself. How? See, by doing it we can see v1 bar plus v2 bar is equal to 1 0 minus 1 plus 2 1 3. Adding these two vectors, it is equal to 1 plus 2 0 plus 1 minus 1 plus 3, and this is further equal to 3 1 2. 3 1 2 is a vector which is given as W bar in the problem. So v1 bar plus v2 bar is resulting to give the vector W bar. Therefore W bar is equal to v1 bar plus v2 bar. That means W bar is a linear combination of v1 bar, v2 bar. Therefore W bar is in the span of v1 bar comma v2 bar. That means w bar can be written as a linear combination of only two vectors v1 bar and v2 bar also, and that is how w bar is in span v1 bar comma v2 bar. So with this I remind for the today's class, and next class let us solve some more problems in the next video lesson. Thank you.